Okay, welcome to the third and final installment of the electrical resistance guide sheet. That's number 3 in our checklist. This is all about using um, the nature of potential difference in the circuit to calculate the various resistances and compare them in a simple circuit. Okay, a couple of things from the information above. This is the symbol for an electric resistor. So it's just a line and then some squiggles. It's no specific. It doesn't have to be exactly a certain angle. Just gives you the concept that as an electron goes in, it's going to have to fight its way through. It's not going to be able to just zip right through. The wire is just a straight line. So when we think about wires, we think of them having zero resistance. They don't. They actually have a small amount of resistance, but usually it's so small in short, small circuits like we're building that it's not really easy to measure. Another thing is this idea of the loop rule. Again, batteries, power supplies put energy into the charge. That's called the potential difference. It's a gain of potential difference. As you go around the circuit, then that means you have to use up all of the energy that an electron has to use up all the energy that it got in the battery. So those potential differences we call potential drops or voltage drops. Again, potential difference and voltage are used interchangeably. I don't like the word voltage. It's not very descriptive. It's just a person's name. The idea of potential difference, again, like falling from a higher height. You had a higher ability to do something in the future. You had a higher potential, and you fell and you got to a lower point, so now you have less potential. It tells us that we're using up our potential energy to do something else. Same basic idea with resistance and current and potential difference in electric circuits. So better term than voltage. Okay, so we're just going to calculate the resistance of this particular circuit on the left and the one on the right. We're going to use Ohm's law. In this case, we're looking for the amount of resistance, so we're looking for R. So R is going to be the top one, delta V, potential difference, that's supposed to be a V, divided by the current. Again, current is symbolized by I. So don't let that confuse you. It's not really that complicated. Just get used to it, and you'll be okay. Okay, in our case, we're putting in 12 volts, so it's 12 volts of potential difference. That's the measure of the energy we're putting in. It means we're putting in 12 joules of energy for every coulomb of charge that moves around. And then 2 amperes is the amount of current. So 12 divided by 2 is going to give us 6. And when we divide volts by a current, we get 6 ohms, symbolized by the Greek letter capital omega. On the right-hand side, ratios are really good in electric circuits. So if you just think about what's the comparison of number 1 to number 2 or number 2 to number 1, it might help you rather than trying to calculate things all the time. If you look at this one, we have the same voltage, but 4 amps. That means twice as much current. Now, current and resistance are inversely related. It's harder to get through when the resistance is high. So we have twice as many amps getting through. That's an indication that we would have half as much resistance. So our resistance should be 3 ohms. Well, let's check that idea using the equation, but don't think you have to do an equation every time. Just try to think, relate, compare things to each other. So we're going to have R is equal to delta V over I, so 12 volts over 4, and that's amps. Oh, look at that. It's 3 ohms. We were right. Okay, so ratios are really helpful when you're trying to analyze electric circuits. Take some time just to compare. If one thing doubles, that means probably something else is going to be cut in half or something else is going to double. It's simple increases and decreases. No squares. You don't have to worry about inverse squares like in gravity or electrostatic forces. So give that a try. Okay, number 10, we're going to use an arrow to show the current direction in both of these circuits, and we're also going to calculate or fill in the blanks. So this might be a little more difficult than the last one, but we'll see what we can do. Okay, so again, current always is pushed out from the negative terminal of the battery. It has its highest potential at that point. In fact, it would have a potential of 12 volts at that point. Now here we have a blank. Let's go around the circuit and see what happens. We continue around the circuit. Now here's a resistor which is going to get in our way, so it's going to have a resistance value, but let's keep going around the circuit. We're not really ready to figure that out yet. We go down here. Now we have 4 amps of current at this point. Now as I went from here, wires really don't change the potential, so there's no potential difference between those 2 points, so I still have 12 volts. When I go through the resistor, I'm going to lose a certain amount of that. We'll figure out how much in a second. And that goes in here. Now there is only one way that the current can go. Since there's only one way that the current can go, and current is made up of charge, and charge is a fundamental property that is conserved, then the current is the same everywhere. So now I can say this is 4 amps. Oops, sorry, I got the amps there. And now that I know 4 amps goes across this resistor, and I know that the potential difference, there's only one resistor in here. Now if you look at the loop, there's only one loop. I'm adding 12 volts here. There's only one other thing that will use up the energy, and that is the resistor. So that means its potential difference, its drop, is going to be a loss of 12 volts. Now for our calculation, we don't need the negative sign, but you should realize that that energy is going to go out. That means when you're working with the resistors, they're going to get hot, so be careful. In terms of the actual value of the resistor, R is going to be delta V over I is going to be 12 volts over 4 amps. That looks familiar. That's the same 3 ohms we had up above. Okay, so that's the very basics and beginning of analyzing any electric circuit. If we look over at this one over here, they've configured it a little bit differently, but it's essentially the same. Some things to point out. The A's here stand for ammeters. Okay, meter, measure. So those measure the amps, the current. That's why they're a big A. To be ammeters, they should have almost no resistance. So again, we're not going to consider them to have any voltage drop. They're just going to be measuring devices. We're going to assume they're perfect and have absolutely no resistance whatsoever. So again, this would not be a change in resistance, a change in the potential. This would also not create a change in potential. It's like the wire. Another is the symbol V there. That's voltmeter. Okay, that means we're measuring the potential difference in volts. Since it's a difference, you'll notice that it has to be on 2 different places of the resistor. The ammeter is actually within the wire. It's part of the circuit. And that's because it measures current, and the current needs to flow through it. So they're actually used in exactly the opposite way. To make it be correct, the voltmeter needs to have infinite resistance. And that way no charge will actually flow through it. So ammeters have 0 resistance in a perfect world, and voltmeters have infinite resistance. Voltmeters are always placed across 2 points, and they will measure the difference in potential between those 2 points. And then the ammeter will be in the circuit and will actually count the charge that's going through, and in a way count the electrons that are moving through that space. Okay, so this one we're going to flow this way this time for our current, because the negative is on this side. This is going to be our highest potential. That's 12 volts. Again, the ammeter doesn't use up any of the potential difference. The voltmeter doesn't use up any of the potential difference. So that means all of the potential difference loss has to be here in this one resistor. So this is going to be a loss of 12 volts. Since we know that the current, there's again only one loop here, so the current has to be 2 amps everywhere. So we can now calculate the R as delta V, 12 volts, over the current I of 2 amps, and we have 6 ohms. Now again, we could have kind of ratioed that one out in that over here we have the same battery, and we're getting 2 times the current. Well, if we have twice as much current over here, that would indicate that this would be half as much resistance, because they are inversely related. So we should have had 3 ohms should be half as much resistance as this one. So 3 is 1/2 of 3 is 1/2 multiplied by 6. So 6 is the correct answer. So again, you can also ratio that out. You can think it out. You don't have to apply the equations. Don't get tangled up as it's got to be a mathematical exercise. Try to think it through. You will be much more successful with circuits if you treat them in a big picture kind of way and don't get tangled up in all the little individual mathematics. Okay, so that's our first look at figuring out the different potential differences and currents and resistances in simple circuits. As we move on, we'll look at the energy that's changed, and we'll talk about the rate of energy change and power, and then we'll be able to actually look at combining multiple elements together into more complex circuits.